Hello.
Recording? Yes, we are. Thank you, Mark. All right. First things first, welcome to this review seminar. I understand this is a relatively small class, but still, it's going to be nice to have this seminar. I took this course, I think, last year, around the same semester as you guys, so I very much understand that for this course, firstly, there's a lot of intuition that's needed. And secondly, it's very much that it builds off of itself. So if you don't get some of the earlier concepts down pat, you will really struggle with the later ones. That being said, my name is Bob. The pink mouse you see on my screen floating around is Mark. And we're going to be running this review seminar. It's going to be 3 hours. The plan for the seminar so far is that we are going to go over some of the more touchy subjects, especially some of the ones that maybe before the midterm you weren't as solid with, and then things that you haven't had a chance to be really quite examined on. So for me, I'll be in charge of starting us off with tautological implication and deductions in zero order logic, and then we will add on soundness and completeness, and then we'll expand that into the same things in first order logic, as well as some first order deductions and I deductions. And then after that, we will take a short break. Mark will take over, and he will go over definability in structures, as well as homeomorphisms, isomorphisms, and the such. Uh, I currently have, I believe I have the raise hand notification on. So if you have any questions during this, and I'll also stop periodically and check that everyone is, following along, then just raise your hand. I'll hopefully hear it. And if not, type it in the chat and I should see the notification as well. So yeah, let's get started. So we'll start off simple enough with probably one of the first things that you guys ran into during this course, which is tautological implication. More specifically, this would be implication in first order law or in predicate logic, zero order logic. And it simply states, let sigma be from a subset of our well-formed formulas and gamma itself be a well-formed formula. We say that gamma tautologically or sigma tautologically implies gamma if and only if whenever sigma is satisfied by some truth assignment, then the same truth assignment, there should be a dash here, the same truth assignment will also satisfy gamma. If you recall from your courses, to satisfy a set of well-formed formulas means that for all well-formed formulas, actually, let's not use that one. For all well-formed formulas in this set, we have that this truth assignment will satisfy them. And then this means in turn that the truth assignment will satisfy gamma. This, as a concept, is very similar, or sorry, it's very simple, but it is worth like being able to grasp this in terms of breaking down sigma into its sets. The reason being, tautological implication essentially means that we could rearrange the well-formed formulas within sigma to reach gamma, maybe not directly through logical operators and such, but we could definitely at least reach it through some stretch of logic, maybe through the implication of some extra well-formed formulas and things like that. So it is the idea that when we're tautologically implied, there is some relationship between the two, and I'm going to hopefully expand on that through this. But that being said, first order tautological implication isn't, I don't think, too hard to grasp. But moving on to something that may be a little bit harder, hopefully I haven't pressed anything, there we go, is deductions. So deductions, oh, I see a message in chat. I will read that in a moment. Let's see here. Did you mean to write sigma instead of gamma? Yes. Where have I wrote sigma over gamma? Oh, here. Yeah. No, sorry. This should be gamma. This is tautological implication. So given that everything in so if every element of sigma is assigned to true, and we have this tautological implication, then we know that gamma is also assigned to true. I have a weird way of writing gamma, but yes, this is gamma. Yeah, so this is, I should probably add in given that sigma tautologically implies gamma. All right. So on to deductions. Oops. So deductions in zero order logic, if you, well, firstly, they're defined as such. They have to be a finite ordered sequence of well-formed formulas where each one arises in three ways. If sigma proves alpha, then any well-formed formula in the sequence must either arise from sigma, must be, or it could be one of our predicate tautologies, or it arises by way of modus ponens, which says if you have the index between 1 and I, if you have two well-formed formulas between 1 and I being the formula you're generating, such that they're not equal, and one gives you the implication, you can build alpha I. Modus ponens, this is the example, or this is the definition that is given, I believe, by Grinnell, or at least he gave this for my year, is kind of hard to grasp with this definition. The textbook gives a definition that I really like, which is basically saying, suppose we have here alpha j, and we have alpha k. This is just something, right? This is just a well-formed formula. And alpha k specifically is defined as alpha j implies alpha I. Then the textbook says modus ponens, in fact, is a step in the deduction where we say that the set for alpha k and alpha j proves alpha I. This is what the textbook defines as modus ponens. So this might look familiar. This is exactly the deduction theorem, and the textbook actually states this. It states that the reverse of the deduction theorem is in fact just modus ponens. If you remember, the deduction theorem would look something like this. This should be AJ. Oops. Ay, ay, ay. That should be K. All right, it's just moving one of these in. So this is exactly the textbook definition for modus ponens, but you can consider it as whenever we have a statement that has this sort of if operator, if we can find the statement in the front half of the if, we can use modus ponens as a subset of the deduction theorem to achieve the then portion. So this alpha k is kind of equivalent to if alpha j, then alpha I. That being said, there's a very important distinction to be made here, and that is that this here, this implication, cannot be used interchangeably for modus ponens with the two-way which is if and only if. So if you have a statement, for example, let's move down a little bit. If you have a statement, for example, where you have alpha j and then alpha k is alpha j left right arrow alpha I, we cannot use modus ponens on this. This Well, it follows directly if you look at the deduction theorem. The deduction theorem isn't really accounting for if and only ifs, it's only working for, if-thens. So the way, if you want to use the deduction or modus ponens for this, because you will reach points where you do, the sort of rigorous version you have to do is you have to say that the following is a tautology. You would have to say something like, this is where if we have AJ and AI, then this implies that AJ, AI. This is true kind of trivially. You could show either with a truth table, or you could argue that this is by definition one of the tautologies, and then using that, you can perform, I don't know, n+1. You could perform modus ponens on AK to get alpha j given alpha I by way of modus ponens on, let's see, alpha n, alpha k. All right, so this, if you have a situation where you have a two-way arrow, then you have to at least, it's good to utilize this tautology, because especially if you're dealing with a strict TA, or especially if you're dealing with a really long well-formed formula where this isn't immediately apparent, you can use this to break down any two-way arrow into any arrow of its individual direction. But yeah, aside from that, I don't think there is too much extra nuance with deductions. I am hopefully going to build some intuition here, and that is that for a deduction is, let's put it as a remark. A deduction is exactly just a proof, right? A deduction is a proof. For those of you who are doing mathematics or statistics, or maybe you just decided to take theory of computation from CS, you've probably dealt with a handful of proofs. In fact, I think you've all dealt with proofs in Calc 1, Calc 2, and discrete math, probably, pigeonhole principle, all that such. But a deduction is just a proof. If you can remember how we did those proofs intuitively. If you remember how we did those proofs, it was always, the proof always went like, suppose we have something, 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 prove something, 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 right? This is exactly our set of hypotheses, it's the supposition, and then this is our alpha, it's what we're doing, and we want to show that gamma proves alpha. So this is exactly what all the proofs are, and if you remember struggling through those delta epsilon proofs, you would eventually, actually, delta epsilon proofs are higher than first order deductions, but you can still consider them roughly the same. But you could remember struggling through those delta epsilon proofs in your maybe first or second year, until eventually one day a TA comes by during a tutorial and he goes, all right, here's how you do a delta epsilon proof. Step one, you write like, oh, for x minus c is less than delta, then like what, f of x minus f of c. I think I just given the thing for continuity instead, it's epsilon or something like that. And then you find values for c, find c, find epsilon, and then your proof is done, right? These are all steps in your deduction. So this might be alpha 1, this might be alpha 2, this might be alpha 3, this might be alpha 4, and then this is just your alpha we're proving. And it kind of, this concept of deduction, if you have trouble grasping it, especially during an exam or something, it is, I at least find it very helpful to consider deductions to be just a very abstract, generalized version of a proof that you're, currently working with. I don't know how to get rid of this little 23 hours alert, that you are currently working with. And then it becomes kind of a little bit easier to figure out what the next step is. Because if you think about a regular proof is categorized by, okay, we are given, you know, something from supposition. And then by, I don't know, some theorem, we have this, and then you keep on going, and you say like, oh, by this theorem, or then this, and then eventually you reach the actual thing you were trying to prove, and then you just end your proof there. Right. So if you think about a proof in first order or in zero order deductions, they are the simplest types of logical proofs. The proof that I think Grinnell likes to use in lecture is the proof that I think it's a matrix is invertible if it has a non-zero determinant. So for example, we know that saying if the determinant is like, I don't know, a matrix A is non-zero, then there exists an A inverse. This is an element of the tautologies. Tautologies, they aren't exactly the same in zero order logic, but they both start with T. It's useful to think of these kind of like theorems. And then suppose our supposition was literally just the matrix A, right? Like maybe the supposition, this is the exact definition. Then the proof would be something like, oh, we know another element of the tautologies is calculating calculating the determinant of A from A. This could be, there's many forms they could take. This could be, you know, you could be taking regular integrals, you could be taking Lagrange integrals, or Lagrange integral, you could be taking different forms of determinants, all that stuff. But this is also an element of the tautologies. And then you use that. This is maybe your alpha 1, this is your alpha 2. And then you say, okay, well, using alpha 2 and A, right? So you say alpha 3 equals the determinant of A, which is by modus ponens, on A itself, which is, let's say this is, this should be alpha 1, this should be alpha 3. Alpha 4. Maybe this is your alpha 2 equals A, by modus ponens on alpha 2 being A, and then alpha 3 being the method to calculate the determinant of A. We get the determinant of A, and then we move down. We say, oh, hey, we notice that the determinant of A is non-zero. Then alpha 5 says that, or is from the tautologies, we say that for there exists an inverse, and this is by modus ponens of the theorem itself. And then the determinant we just calculated. And then we notice that this is exactly what we tried to prove, and so our proof ends there. But yeah, this is the intuition that kind of exists for proofs, or it's the intuition that is helpful to build for proofs. Because if you think of deductions themselves as proofs, then the next steps become very clear. And so with that in mind, there are a few proof methods. Like this is a very simple proof. It's a proof by definition, proofs by theorems, all that stuff. There are a few more complex forms of proofs that I am going to give as an example. And so I want to give these as an example because, well, for one, they're harder to wrap your mind around, but I want you to see that more complex proof methods, specifically like proofs by contradiction, they can still be done in this sort of zero order format. Before that, though, I want to check if anyone has any questions or anything, and then I'm going to move on to soundness and completeness. So is everyone able to sort of follow along here? Let's see if there's any questions. All good? Okay. Following. Sweet. Okay. So before I get a little bit ahead of myself and start doing some examples, I want to introduce the concept of soundness and completeness. Now, well, I want to say introduce, but you've all probably become very familiar with soundness and completeness, given the fact that, well, given the fact that you probably spent a very long time, doing the proofs for these things, especially for completeness. I know one side of the completeness proof is incredibly difficult, but I'm gonna gloss over soundness and completeness as a sort of intuitive thing and what they mean intuitively. So soundness as an intuition should make sense, or make sense in that if we have something that proves a statement, then when all our suppositions are true, then that statement should also be true. That should make sense intuitively, where suppose one day in lecture, right, we might do this half. Let's say this is the first half of the soundness theorem, and then this implies second half. The first half of the soundness theorem might be like in lecture, we introduce a topic or maybe a theorem. Let's say not a topic. Let's say we introduce what do they call it? They call it a claim. We introduce a claim. And then you spend the rest of lecture proving it. Right? And then by the end of the lecture, the teacher goes, all right, and that's the proof of the claim. We now know that's true. You can, study for that for your exams or whatever. And then you go to your exams and you see all the conditions for our claim. They are true, are fit. Then you think, oh, well, we already proved this to be the case in lecture, then let's use our claim. Maybe if you have a particularly strict professor, he might ask you to prove it again. That gets back to completeness, but yeah, the idea is that I remember I mentioned earlier, tautological implication means that when all of the well-formed formulas in sigma are true, then gamma is also true. So if we can prove that the well-formed formulas in sigma prove gamma, these are our suppositions. To say that tautological implication claims these are true means our suppositions are true. And if our suppositions are true, then what they're proving is true. So this is basically saying that the soundness theorem is applying the knowledge of what we prove. Once we've proved something, we can then use it, basically. This is what soundness theorem is to me. And completeness theorem is the exact opposite of that. Completeness theorem says, let's say this is A implies, oops, ooh. Let's say this is A implies B again. Completeness theorem says, let's make a claim. So claim some, this is A, property. Maybe we notice, hey, when all these things are true for a specific case, then, or maybe a specific number of cases, then this is true. So let's say this is from logical inference, from logical operators. So suppose maybe we say, hey, all these matrices have, non-zero determinants and are invertible. Like, hey, isn't that weird? All of these matrices have non-zero determinants and they're totally invertible. Well, what if we claim that this is true for all of them? Well, then let's say these are true and we know this is true. I wonder if there's a reason for that. B is find the reason or prove your claim. So that is what soundness and completeness do in theory. Now, completeness is a way more complicated beast than soundness. Soundness is, as the name suggests, very sound. Most areas of math are sound, and that if you can prove it, then it's always the case that once you meet those same conditions again, the same things apply. However, completeness, and I'm not going to write this part down because this is more of a side tangent. Completeness is a different beast in that math is not necessarily complete. You might have noticed it in the lecture calendar, but I don't think Brunel ever gets to it. One of the things that's mentioned in this calendar is something called Gödel's incompleteness theorem. And the incompleteness theorem states that for any reasonable system of hypotheses, there are statements that cannot be proven even if they are true. So you don't have to worry about this for your exam, but these statements are mostly self-referential. The famous example is the sentence, this sentence cannot be proven. It's an unprovable statement, but it's self-referential. So the idea of completeness states that if something is true, we might not be able to prove, or we should be able to prove it. And in most orders of logic, in zero-order logic and first-order logic, that holds to be the case. But another way you can think of soundness and completeness as a whole is sort of informally. Soundness is a mapping from tautological, sorry, not from tautological implementation, from proving to implication, whereas completeness is a mapping from implication to proving. So, for example, if you have a theorem, or if you're trying to prove something that uses implication, but you only have provability, then you can use soundness to map that over directly to implication. And then vice versa, if you have implication, but you need to show something by proof, then you can map that over. This format is especially, I believe it is used in the proof of soundness. Or not sound, it's used in the proof of completeness. If you remember from class, one of the directions for completeness, I think it was completeness, Grinnell goes over and he says something along the lines of, oh yeah, well, now that we have the soundness theorem shown, we can prove the direction of completeness by mapping back over to deductions. And then once we have deductions, we show such a deduction exists, and then we map back, and then we have that direction for implication. In fact, actually, if you prove, the reason I'm not sure is because if you prove, depending on which version you prove first, you can use one to prove the other. So soundness will prove one direction of completeness, and in the same way, completeness will prove the same direction for soundness. So, that being said, I see there's a question. I have been told you can consider next term if you wish to learn incompleteness. Ah, okay, there you go. If you want to take philosophy C51, symbolic logic, then there is a more concrete term for completeness. Yeah. Adjacent and interesting course. Yep. Yeah, honestly, completeness is an interesting thing. Completeness in math is very obnoxious because the way that I believe Gödel proves incompleteness is he goes something along the lines of, let's convert all of these mathematical symbols in these well-formed formulas into numbers themselves, and then we can show that we can do math on those numbers, and if something is provable, then the numeric adaptation of that statement should arise from our statements, or something like that. You don't have to understand that perfectly, but that is roughly what it means. Anyway, down to deduction theorems. I mentioned earlier, deduction theorems should look familiar. If you do a deduction theorem backwards, specifically if you do this one backwards, right, you look at this direction, is modus ponens. So we say that remember, given A implies B, alpha implies beta, then if alpha is true, we have beta, right? This is exactly the format for modus ponens. This means that going backwards is modus ponens, but this is also useful, maybe not in zero order deductions. I see we have another message. Oh yeah, we have, even though this isn't as useful in zero order logic, the deduction theorem is very useful in first order logic, especially with the ever terrifying monster that is I deductions. And actually, I'm going to end off my section later on with an I deduction that uses this deduction theorem. So useful in I deduction. Let's see. I deductions, they are way stronger than formal deductions, I think, because you can get way more out of them. In theory, they're the same. In fact, when I spent like an hour or so trying to figure out the solution for one of the I deductions, and I couldn't get through one of the meta theorems they used. And so it took a little bit, but you can just expand it and decompose it into formal lines in a deduction. But I'm not going to go through that. Anyway, let's go through a good example of a deduction in zero order logic. I don't know. I should also mention, these are taken from previous exams that Mark and I took. We basically, for the ones we got right, we just have them. And then for the ones we got wrong, we went back and we resolved them. So this one specifically is as follows. The deduction theorem for zero order logic states that if sigma with the inclusion of gamma proves beta, then sigma proves gamma, or if gamma, then beta. Let sigma, this should be, I keep saying sigma, anyway, yeah, let sigma be a non-empty satisfiable subset of well-formed formulas, and let alpha be a well-formed formula itself. Sorry, my participant screen just popped up. All right, be a well-formed formula itself, and assume there is a contradiction K such that sigma and the negation of what we are trying to prove arises a contradiction. Use the deduction theorem to prove that sigma proves alpha. Use any tautologies you deem reasonable or justify them. So this should look immediately obvious. Firstly, a contradiction, I don't know, is ever sort of strictly defined, right? Let T be an element of the tautologies, then the negation of T is a contradiction. A contradiction essentially is always false, right? The truth assignment for not T equals false for all truth assignments. So that's what a contradiction is. And so if we want to read these using our intuition of the fact that deductions are just representations of proofs, this is just saying, well, suppose we have all of our suppositions. Suppose that what we are trying to prove isn't true. And suppose that that means we have a contradiction, right? This is exactly a proof by contradiction. When we do proofs by contradiction, the question would be something along the lines of, oh, prove this statement here. Maybe I'll call this X to be more concrete for this example. Prove the statement X. And then we say, okay, well, by way of contradiction, suppose instead, so instead of trying to prove it, we now add it to our list of suppositions. Suppose that X isn't true. And then you do the proof, and then you eventually say, oh, well, this gives us, 1 + 1 = 3, and that's bad. It's bad, it's stinky. And so, therefore, X is true. This is exactly that. This is a proof by contradiction. Not only that, once you solve this problem is showing you that a proof by contradiction is logically sound. So let's go over the actual solution for this. The first thing we note is that we want to show, there it is, want to show that there exists a deduction D, which is an ordered set. I use gamma here because alpha is already being used. No, I use alpha, never mind. Such that alpha 1, alpha 2, all the way up to... Are we allowed to show that proof by contradiction works using a proof by contradiction? That would be a little bit self-referential because you are assuming that a proof by contradiction is concrete. You can prove this without that. In fact, I found it a little bit easier because they kind of give you half the proof already. So, yeah. So we want to show that there is a deduction where, you know, standard things apply. Alpha I is an element of a set of things, or alpha I is an element of the tautologies, or, and I'm going to use, okay, so or alpha I comes about by modus ponens. Oops, this is not an alpha. Comes about by modus ponens on alpha j, alpha k, where, you know, 1 j k less than I. Okay. And then we want to show finally that alpha n is exactly alpha. All right, so how do we go? We are given where is it? We are given that sigma with the inclusion of not alpha proves a contradiction. So then by the deduction theorem, more specifically the deduction theorem for proofs, we have that sigma will at least prove on its own that not alpha implies this contradiction. Let's move down just a little bit. Thus, by definition of deduction and provability, thus, there exists a special deduction, and here's where gamma comes along, which I will call gamma 1, gamma 2, to gamma m, where gamma m is equal to this statement. Right? This is true by definition of deductions. Now, I'm going to make a claim here, and this is something you're going to have to do at least a few times during your exam. I'm going to claim that the following is a tautology. I'm going to claim that the negation of, this should be alpha. The negation of alpha implying some theta is equivalent to, actually, I'm going to do a little bit weaker. I'm going to say implies that the negation of beta implies alpha. This is contrapositive, right? This should be immediately obvious. It's contrapositive. I'm gonna claim that this is an element of the tautologies. I'm gonna prove this, and I think for cases in your exam where you only have, you know, 1, 2, you only have 2, I guess, symbols in your formula. Symbols could be, you know, either other well-formed formulas, or they could be letter symbols. Then it is fine to proof by truth table. Single arrow implies it is two ways, but I think I showed way up high here. If you want to use the two-way implication, you cannot use this for modus ponens. You have to deduce it down to the one-way. So the two-way does imply the one-way. So, I can use the two-way, actually. I will use the two-way in that case. And then I'll just add on the extra step. It's getting bigger as I go. Anyways, single arrow implication, right arrow. Oh, yes. Yeah. Oops. Yeah. Yeah. So it's better to drag it's like you said, it's better we use tautologies to break down two-way arrows. I'm going to claim this is the case. So let's say now we have our truth table by truth table. By the way, all of this stuff, the reason I'm not erasing all of it, I will provide the meeting recording at the end of this. I'll send it to Grinnell and hopefully he'll post it. But I will be downloading this entire thing as a PDF. I apologize, you're gonna have to like zoom in and zoom out a lot because the nature of this whiteboard, as you're kind of moving around, it gets bigger and bigger. I've used this whiteboard a few times and every time it's happened and I haven't broken that habit. Anyway, proof by truth table. We have values for alpha, we have value for beta. It's good to break these down. So we have a value for not alpha, we have a column for not beta, and then we have a column for not alpha implies beta, and a column for not beta implies alpha. So different ways that alpha and beta can happen. Both are true, one's false. One's false, one's true. Both are false. Well, this follows immediately. This is false, false. This is false, true. This is true, false. Let me know if I make an error anywhere. I'm going by this quite fast. True, true. Now, here, false. This is true vacuously. Same here, true vacuously. Here, if this is true, and if this is true and this is true, then this is true. Same thing, this is true, but this is false. This is the only time that implication falls apart. So this is the case where it's false. Here, not B is false, so vacuousness, this is always true. Same for down here. Not B is true, and alpha is true. Then this is true. Not B is true, but alpha is false. Then this is, again, the only time alpha is false. And then we see here, if this is the statement that we're trying to prove, then we look at these and we say, okay, true, true is true, true, true is true, true, true is true, false, false is true, right? False is vacuous. So therefore, this statement here, which I'm going to call, I don't know, beta. Beta is an element of the tautologies. I shouldn't use beta. We're already using beta. Running out of symbols. Psi, we use phi. So therefore, this is phi. Phi is an element of the tautologies. Now then, now that we have this, by the way, is just one side of the contrapositive. The contrapositive, if you just want to use that, I don't think you would have to prove it, but this is a particularly finicky tautology. It's nice to prove. So therefore, we have that this is a tautology, and we are so assume that beta is equal to the contradiction because we only have that beta is a well-formed formula. We have this is part of the, then we have that not alpha giving us the contradiction is the same as the opposite of the contradiction, giving us alpha. And from here, the proof becomes immediately quite clear. So let's say, and actually, I'm going to go back and go over this step once we get to I deductions, because this is a very interesting step that I've done. But let's say now we build our deduction, right? The first m steps of our deduction D are as follows. Or actually, not as follows, are exactly the first steps of, where is it? The first steps of this are exactly D prime or D star. Because we need this, we need these. So we have that alpha, oops, we have that alpha 1 is equal to gamma 1, alpha 2 equal to gamma 2, all the way down, alpha m is equal to gamma m, which is equal to not alpha proves or gives the contradiction. We know this is a valid deduction. And why do we know it's valid? Because the professor gave it to us. Because given. Now, what is the next step here? Now we can say, okay, alpha m plus 1 is equal to psi, or equal to phi. Phi is an element of our tautologies, and specifically, we just wrote down that it is equal to not alpha given k implies not k gives alpha, right? And then that means m plus 2 gives us not k gives alpha by way of modus ponens on alpha m and alpha m plus 1, right? Because we have this as proven. That happens to be exactly this side here. That gives us this. Now, the next step is done by definition of contradiction. So recall that a contradiction is the negation of a tautology. And so therefore, the negation of a contradiction is the negation of the negation of a tautology, which cancels out. And it ends up being a tautology. So this means that the negation of any contradiction is an element of the tautologies. We can prove this by truth table. Prove by truth table. What's the only assignment we can give a contradiction? It's false, right? Contradictions can't be true, so therefore true. Done. Now, therefore, suddenly now we have not k and we have this. So alpha m plus 4 is alpha by way of modus ponens on alpha m plus 2 and alpha m plus 3. And that is exactly the contradiction we're looking for. We see that this deduction exists, therefore deduction exists. Therefore, sigma proves alpha. Is everyone following along for this? Does it make sense? Are we all good? Making sure. Looks good. All right, sweet. So yeah, this is about as complicated as I think deductions will be on your exam. You have probably encountered something similar, if not the exact same question. Grinnell doesn't really post his previous exams from what I could tell, so I literally just pulled this from my previous midterm. Can we use soundness and completeness? For this case, No, I copied this uh, from his exam, and his exam comes with the note, do not use soundness or completeness. But in the case that he leaves that out, then yes, you could use, I believe it is soundness. Yeah, life is very easy with soundness. You use soundness, you put this back into the terms of tautological implication, and then you can show that sigma tautologically implies alpha, and then with completeness, you can map that back into sigma proves alpha. So yes, this is so much easier without or with soundness and completeness, but without it, it teaches this very interesting lesson of, hey, proofs by contradiction, they actually do work, and this is why they are logically sound. And furthermore, it teaches this interesting skill, which is if you're ever without soundness and completeness, and we are given in our supposition that something is provable, then we can use the existence of that deduction as part of our deduction. This actually is an adaptation. This is the closest thing you will get to a I deduction in zero order logic. I deductions don't really exist in zero order logic because there's not enough theorems to go about it. But like if we are given that this is true, we are essentially using the fact that this is true to prove this. And we would consider it an I deduction. Life is indeed incomplete without completeness. Now then, let's see what is next on our agenda. Ah, sweet. Now we can get into first order logic. So I'm going to take first order logic kind of in stride, where we're going to define an assignment function first. So assignment functions, they kind of follow the same. How do I disable this? Assignment functions, they kind of follow the same as in zero order logic, where assignment function with the language U or language L and structure U is a function this time that instead of mapping alphabet terms to something, it maps variables to the universe being anything that can be defined by what is given by U, where V has an infinite amount of variables and the universe is non-empty. And then again, we can define an extended one to be a term. Terms are, of course, things like functions on variables and such. It follows almost the exact same as an assignment function in first order logic. It's just now we have different terminology. No pun intended. But what is different is satisfiability. So if we recall from zero order logic, zero order logic, we have that this is the case if then if is satisfied, then alpha is satisfied. Right. And here, satisfied means that if a TA V assigns, I can't spell assigns, assigns all elements of sigma to be true, then that same assignment should assign alpha to be true. Right? This is what it is in zero order logic. First order logic is the exact same, but satisfiability is much worse. It's way harder to get to. Right? First order satisfiability is picky. So what is first order satisfiability look like? Right? We say that something has to be satisfiable under a structure and a specific assignment function, same as in zero order logic, where we're looking at a single assignment function. If the following 5 things hold true, that's right, this is a big image. First one, if T1 and T2 are both terms, then this is satisfiable. This is our term for satisfiable under the assignment S, only if the assignment maps both T1 and T2 to the same value in the universe. These all technically make intuitive sense. I'm going to use that term a lot. If their assigned values are equal, then this is equal. Now, the reason we have to use this kind of definition is because we have to recall that T1 and T2 are meaningless with that until assigned meaning. So quite literally, we do not know if this is true. This is unknown to us until we assign the values, right? This is conditional on the fact that these assign the values. So we can't say this because someone could go and say, oh, well, what if my truth assignment assigns T1 to 3 and T2 to 1? Well, then suddenly it falls apart. We have to use a different assignment. Okay. T is an n-place predicate. Then the n terms T1 to T for the n terms T1 to Tn. Then the predicate for T1 to Tn is true if and only if T1 to Tn are part of the predicate set for P. Now, if you have a hard time grasping the predicate set is the set of all, for those of you who do computer science, or actually not even computer science, for those of you who have coded in Python, you might have heard of the concept of a tuple, right? In Python, a tuple is stored as like xy. It's often returned in a function. And then you say like, oh, we'll store x and y as xy. And then suddenly you have 2 variables and they have their 2 individual meanings, right? That's what a tuple is in Python. So I'm going to use the terminology here, but a tuple is basically just a collection of things. It's all n tuples that satisfy P as a relation. So let's give an example here. An example is to be, suppose P is equal to, suppose n is 2, firstly. Suppose n equals 2. 2-place predicates are the easiest for us to grasp. And P is greater than. Is the relationship greater than? Then the predicate set is simply all of the 2 tuples where x is greater than y. So anything that fits a relation appears in the predicate set. So this means that if our terms satisfy the relation, then assigning them that value will give the will make this hold true. And in fact, I think there's a typo here. I believe these should be assigned values. So these should be Ti, not Ti. There you go. These should be assigned values. That's a typo on my part. So once we assign them values, if they appear in the predicate set, then this holds true. Now then, let gamma, alpha, beta be well-formed formulas and assume that we have some sense of satisfiability between all these. Or we have that these are all satisfiable. Well, we've only defined satisfiability for terms. Like this is a term here, this is a term here. Why did we make this jump? This is the same as like a definition by induction, informally, quote unquote, where because terms themselves are well-formed formulas, we can say that we have three well-formed formulas at least, which are all terms where this is true. So negation. Negation is simple enough. If we want to show that the negation of something is satisfiable, then we cannot also satisfy the well-formed formula itself. This is the equivalent of saying if A is true, then we cannot have the case where negation of A equals true. All right, it's the same concept. This is in zero order. Same here. A lot of these sort of logical operators, they are just being broken down. There is almost a sense of distributiveness in satisfiability in first order logic, where if we're trying to satisfy first order well-formed formulas, we can almost distribute that satisfiability into the operators themselves. So this is the best example of it. There is no real other intuition. If we distribute the satisfiability into A, if A then B, we get if A is satisfied, then B is satisfied. Right? Even saying that out loud, it makes sense. But this means that this in itself here is a well-formed formula in predicate logic. I'm going to do it here. This is a well-formed formula in predicate logic. And so that means that this here, A, maybe this is B, right? A and B are sentence symbols. Wow, I really can't spell today. So if we suddenly collapse this back into zero order, if we can show that alpha is satisfiable, then we know that beta is satisfiable. If we show that alpha is not satisfiable under some structure, then this statement's always true. It's vacuous. Same thing applies for other operators. We have the AND operator, the OR operator, or the two-way single arrow operator. All of these function just by distributing the satisfiability in first order logic into the actual statement. And in doing this, we collapse these into a zero order well-formed formula where this entire thing is just a well-formed formula in predicate logic. Now then, we have a very different thing here. We have the for all and there exists operators. These things here are introduced by first order logic. You can think of the sort of hierarchy of logic, like orders of logic, as the next order of logic is the exact same as the previous order, but we add on a few extra things. And then those extra things mean that we have to redefine all of the things we previously defined. So between zero and first order logic, we introduce the idea of quantifiers. Quantifiers here mean that we have variables that can take on multiple meanings. And so we have to redefine our truth assignment or our assignment functions to go from true or false to their meanings. And we have to introduce the idea that for all possible meanings, or there exists a possible meaning for some variable. Now, the truth assignments here, rather than using the regular assignment, uses this. And we've given the definition for this. What this means is that normally, when we assign a value, let's look at there exists. Normally, when we want this to be true, we know that this is true, right? Informally, this is true or satisfiable, if I want to be concrete. for some specific value, some specific assignment of X. And so we're just saying, well, let that assignment be exactly D. And then we show that whenever we are assigning something, if we assigned X, or if we assigned a Y that is an X, these should both be Y. If we assign a value of Y that is an X, we don't care what the assignment is because it doesn't appear here. But if we're assigning the variable X, we must give it the assignment D, because only then is this true, right? This is the exact, there exists D. This one means that it's true for all possible assignments of X, which means that for all D is not saying that we are free to choose whichever. It means that this must hold true, holds true for all items in universe. It holds true for all the items in the universe. And so for each one of them, we check that it works. This is the same as breaking down a there exists and just doing the there exists for every single element in the universe. And if we can see that that holds true, then it works for all X. So using these, we now have some idea of satisfiability. And this sort of notation is chosen very purposefully, such that satisfiability under a structure given an assignment looks similar to in first order logic if something is satisfied by the empty set, i.e. it's like a tautology or something. This is not concrete, but yeah, it looks like it follows similarly where it is satisfiable. That's not a tautology, I realize, but yeah. Now now that we have a way of defining satisfiability, we can actually just go and pull that definition from zero order logic into first order. That definition of tautological implication, it follows the exact same. And in fact, to show that, I'm going to go back up and I'm going to take the definition of first order tautological implication, and I'm going to put it down here so we can compare them. So we notice tautological implication in first order logic says that we say sigma satisfies phi if and only if for all structures and assignment functions, we observe that if it under a specific structure and assignment function, that all of gamma is satisfiable in sigma, then phi is also satisfiable. This should look the exact same because we're saying here that if everything in sigma is satisfied, but this time in first order logic, then what we're trying to show is satisfiable is also satisfiable. So I could say this is A, this is A, and then this is B, and this is B. And the idea that we have some truth assignment here, this maybe we consider this C, this is the same as for all assignment functions or for all structures and assignment functions if one of these works. So we're not saying that it's going to work for all of them, but in the cases where one case of these two satisfies sigma, then it will also satisfy gamma. So yeah, these are direct these are direct mappings of each other. It's just, as I mentioned before, once we add in more concepts from first order logic, we now have to redefine what it means to be satisfiable. This is our new definition for what is satisfiable, our new definition for our conclusion being satisfiable, our new definition for some truth assignment. now truth assignments are attached to structure. So it also has to be true for some structure, right? We just have to keep adding things on to make these true. And that is tautological implication in a nutshell. With tautological implication, we have something called validity. Validity is a very small topic, but it's useful to mention. And that is that a valid well-formed formula is a well-formed formula that is satisfied for all structures of a language and all assignment functions S. This here should look familiar, something that's satisfiable for all assignment functions. We look back into zero-order logic. What's satisfiable for all truth assignments? Well, that is a tautology. This is the analog of tautologies in first order. Ooh, I'm running this space. In first order logic. It is an exactly equal definition. So this becomes more important once we define deductions in first order theorem or in first order logic. But before that, I want to kind of go into a very interesting concept here. And this is the concept of modeling. So we say that for a single structure U in the language L, we say that U models a well-formed formula gamma if all assignment functions we can possibly define on U will satisfy gamma. Now, I don't know if Grinnell goes over this example in your class, but he mentions it in ours. The idea of modeling here can represent fields of mathematics. So, for example, I believe he uses the definition of group theory. We have the group theory axioms. I don't know the group theory axioms, but I know there should be 3 of them. But suppose we have the group theory axioms, lambda 1, lambda 2, lambda 3, right? Now, we recall what is a structure? Well, the universe of a structure is anything we can make from the signature of U. Right, so I like to think about the universe as this all-encompassing set of just building blocks. They are just building blocks. They are the like observed values that we can replace our arbitrary abstract values with. Right. So then therefore, if we have, I'm going to give these all the subset G. Therefore, if we have some well-formed formula phi of G, which is equal to axiom 1 and axiom 2 and axiom 3, then if the universe U models phi G, then U is a group, or it represents a group. So what does this mean? This means that we now have a meaningful way of categorizing mathematical objects into fields of mathematics. And when I talk about fields of mathematics, I'm not talking about field theory, like finite fields and such. I'm talking about like geometry, group theory, statistics, calculus, set theory, all that stuff. Those are areas of study in mathematics. We now have a way of categorizing things into their areas of study. It also means that suppose, and actually another good example is the probability axioms, right? In probability theory, I'm a statistician, so I know the actual 3 probability axioms. We have things like, oh, axiom 1 for probability is that all probabilities are between 0 and 1. Oops. Between 0 and 1. Axiom 2 for probability states that the probability of the entire sample space is equal to 1. Axiom 3 states if A, B exclusive, then probability of A union B is equal to probability of A plus probability of B. Things like that, right? These 3 things form the foundations of probability theory, and they're axioms and not theorems, because these are 3 theorems that are so important that you could derive all other theorems of probability with these 3. So that means that if I had gamma p, which was equal to, we should have G in them. That was equal to the probability axioms. Wow, no. There we go. Equal to the probability axioms. Then if U models gamma p, then U describes a probability measure. So what does this mean? This means that suppose you are working on a problem, right? Maybe you are doing your PhD, you're trying to solve this very difficult problem. But with the tools you have in your field of study, you can't solve it. Like maybe it's incomplete in that set. You cannot solve the problem. Well, suddenly some new development comes out in a completely unrelated field. You look at your axioms and you look at the axioms for that field and you realize, hey, these objects that I'm working with fit all the axioms of that field. They model those axioms. Well, then suddenly that means that not only are you working in your area of study, you're also working in their area of study, and you can now apply what you learned, or like you can apply the results from that area in your own work. This is especially useful, although they might not know it immediately, for theoretical physics. If you didn't know, they recently came up with a new law of thermodynamics, which deals with the internal volume of black holes. And they say that, hey, what if the internal volume of black holes is not based entirely on entropy, but it's based also on the complexity, the quantum complexity of their state? And that is a bunch of big fancy words, but the word complexity stands out because the complexity axioms for complexity theory also apply equally to complexity theory for things like theory of computation. And so they made this connection. They said, hang on, that means we can model black holes with machine learning models. And that's what they've been doing. And so far, the results have been good. And so you can see that it's this weird thing where all of math becomes interconnected by these axioms. And then we can show that they are connected with mathematical logic. So that's a very long tangent there. But using that, we can get into first order deductions. So a first order deduction and also an I deduction are as follows. Now, this once again is the definition that Grinnell gives. I'm normally a fan of the definitions Grinnell gives. They're pretty concise, but I'm not a fan of this one. This one, I think, is a bit over the top because these are all true. A deduction in first order logic is a deduction or a deduction of phi from sigma, where sigma can be the empty set or the entire set of well-formed formulas, is a finite and ordered sequence such that the following are true. All of these are well-formed formulas, and the last element is phi. This is a very small nitpick. It's not a very big nitpick. These things honestly could have gone into supposition because I think it is way more useful to expand this out and say, one, that alpha I is an element, could be an element of the set of hypotheses. 2, alpha I could be from the set of axiom groups. Or 3, alpha I from modus ponens. And the reason I say that is because this mirrors our definition. This is first order logic. This mirrors our definition of zero order deductions, right? If you remember, in a zero order deduction, we have that alpha I can also be from the set of suppositions. Alpha I here is from the set of tautologies. And lastly, alpha I arises from modus ponens. So the reason I draw this connection is the only difference here is this line, the second one. Here, alpha I is an axiom group, and alpha I here is a tautology. This immediately becomes clear once I introduce the first axiom. And of course, that first axiom is, where are we? Here it is this. The first axiom, without reading it off, essentially describes how we get tautologies in first order logic. And that is to say that to get a tautology in first order logic, we are literally just taking a tautology in zero order logic, and we are assigning terms, atomic formulas to it, or well-formed formulas to it, rather than just using sentence symbols. So it is literally just saying, take a tautology in zero order logic, throw out the well-formed formulas, and then throw in first order well-formed formulas. And that's how tautologies arise. And that means that this set here, that means that this set here, which contains A1, right? A1 is a subset of the set of all axiom groups. That means that tautologies are in here. The set of all tautologies in first order logic are in here. In fact, these are equal sets. So yeah, that is where this comes from. So rather than just having tautologies, we now have tautologies plus other axiom groups. And before I go into other axiom groups, I'm going to introduce the concept of generalization. Generalization is simple enough. It says that if you have a certain statement, then alpha is a generalization of gamma, if gamma is just alpha, but with a bunch of universal quantifiers. This intuitively means that if none of these variables appear in alpha, then it's like saying, I don't know, it's the equivalent of saying for all matrices, right? There's a lot of variables in here. 1 plus 1 equals 2. Happy face. That works. Like, there's nothing logically wrong about it. It's logically unhelpful. It's not useful, but it's true. And then we could, if this variable is in our well-formed formula, it's the same as for all matrices. Let's give these a number. Let's give these an assignment. A, we have determinant of A non-zero imply, or if and only if there exists an inverse A. Or and A is n by n. Add that in. Anyway, all right, it's the same idea. This is a generalization. This is inherently fine. This is just extending that to everything else. I realize I'm running a little bit out of time here, so I'm going to introduce the rest of the axioms. First things first, I have given names for all of these axioms. Do not write them down. I made them up. I made these names up because I feel like they help with understanding. So these are axioms 2 and 3. And then here are axioms 4, 5, and 6. Whoops. Let's get rid of this. Here's axiom 4 and 5. And here is axiom 6. I do see 2 questions. I will look at those in a minute. Are there any first order topologies that are more useful than others that we should memorize? Some of these names are used in text. I made them up. It's okay. Math is all made up. Okay. Are there any first order tautologies that are used or that are useful than others that you should memorize? Technically, yes. And you get them by taking all of the useful zero order tautologies. So the tautology of A, not A, contrapositives, breaking down, breaking down two-sided arrows into one-sided arrows. All of those are useful tautologies in zero order logic. You take those and you instead use well-formed formulas in first order logic, and you now have the same useful tautology in first order logic. So yes, there are very useful first order tautologies. The nice thing is you've already memorized them. They're the same ones you memorized for zero order tautologies. So yes, in short. Anyway, these are, aside from axiom 1, which I just defined for tautologies, these are the next 5 axioms. Axiom 2 is the axiom of replacement. If it is the case that for all variables, alpha is true, then we can choose a specific one. This is just saying, okay, well, choose one. And a proof it would be, if this is true for all cases, then choose the case that fits our supposition. This one for all is distributive, looks like this. All right, this is especially useful if X is a member of both these well-formed formulas, it's in the support. If not, then this is equivalent to just B. Axiom 3, the universal statement states that if A is true, or if alpha is satisfiable, then for all alpha is satisfiable. This is like saying, 1 plus 1, then 1 plus 1 is the case for all matrices. These two things here, actually, all three things here actually, are kind of, I'm going to say corollaries with heavy air quotes, corollaries of generalization. Axiom 5, equality of variables. It's pretty simple, it's pretty silly. I've seen it used once, and I saw it used once to deal with commutivity in a proof, but the chances that you use this are very low. Like I saw this in a proof where someone said, I think it was y equals x, and x equals x, and x equals y. It was like in the proof of commutivity or something like that. But yeah, that's where that came up. I don't see this coming up in your exam. Yeah, you have to use A2 for that one, right? Yeah, essentially. But yeah. And then the sixth axiom, the replacement axiom with equality is like the replacement axiom for well-formed formulas, but it's like the there exists version. It's like if we have a there exists X and we can replace it, this is similar to suppose there exists X equals D such that alpha. So this is equal to like there exists X alpha. Then we can replace X specifically with this value. Right, it's similar to that, where if X equals Y, we can replace all or some. Very important, we can say some. We can replace some occurrences of X and alpha with Y. Now, the interesting thing about these axiom groups is, yes, these axiom groups are rules, but you notice that these themselves, like this here, this is a well-formed formula, right? These are all well-formed formulas, right? This is a well-formed formula. This is a well-formed formula. Very simple one, but this is also a well-formed formula. So what does this mean? This means that the axiom groups are sets of well-formed formulas. During a deduction, we can just pull from these. We can just generate any well-formed formula as long as it is one of these, and we can treat it as the zero order analog for a tautology, the first order analog for a zero order tautology. We can just generate useful well-formed formulas like this. Now, this fact here seems very simple. It is incredibly abusable because all axiom groups, or all axioms, excuse me, are valid. So these are the first order analogs of tautologies. I've said that quite a few times. We can just kind of use them willy-nilly. And if we have some really complicated well-formed formula that we're not sure how to get in our deduction, we can generate it as one of the sides of the axiom groups and then just apply that rule and move it onto the other side. So this means that we can really, really heavily abuse this. And I'm going to show that using an I deduction. So before that, here is the definition for an I deduction. An I deduction is a deduction that considers the importation of metatheorems. That is to say, if A then B, if we want to prove if A then B, then it is sufficient to assume A, then prove B. This looks familiar. Or if this sort of example is familiar, that is like saying if we want to prove if A then B, then it is sufficient to prove that we assume A and then prove B. This, right? This is just the deduction theorem. So this is an example. This is not a concrete definition, but what that means is that when we consider these meta theorems, it means that rather than have, actually, I think I'm wrong by my last comment. I think you have to use A6 to get, yes, sorry, it is A6. But for those of you who are wondering, this was in reference to my example of y equals x gives x equals x is x equals y. This was, I believe this actually is in the textbook somewhere, in text somewhere. You'll have to look around for it, but this, I believe, is used in the textbook somewhere. An I deduction basically means that theorems, metatheorems that we can make on deductions and on well-formed formulas, we can use them as actions in our deduction. So what does this mean? This is probably best used or shown through an example. So I'm going to give, because I think first order like formal deductions are pretty self-explanatory. They follow the same kind of logic as first or zero order deductions. So I think it is more useful with the time I have left to give an I deduction example, specifically one that abuses, I say the word abuses quite literally, that abuses the ability to generate any well-formed formula we want from axiom groups, and also uses I deductions, or uses things like the deduction theorem and the generalization theorem to make our lives easier, basically. So let's see, this will be the deduction we're writing. Mark might recognize this. I pulled this one from his final exam. So first things first, for an I deduction, let's use our first meta theorem. Meta theorem, the deduction theorem. That's a theorem, right? Deduction theorem for first order logic states this, right? This is the deduction theorem, right? If we want to show this, it is sufficient to show instead that x equals y, comma, for all z, q, x, z proves for all, oops, for all y, q, y, z. Right? This is the equivalent of, just adding it on. But yeah. So this is the first meta theorem. This means that rather than showing this exact deduction exists, we're just going to show an equivalent deduction and use the meta theorem, the deduction theorem, and just, go from there. So first step in this deduction, easy one to call, alpha 1, x equals y. This is an element of, let's call this, let's call that sigma, element of sigma. Easy enough. Now then, what do we do with this? Well, x equals y looks very familiar to a certain something. It looks very familiar to this. All right, it looks very familiar to axiom 6. So let us generate something using axiom 6. We have axiom 6 goes x equals y implies we can take some well-formed formula and replace some elements. Well, let's generate a well-formed formula that is useful for us. We notice here that in our final result, we have x, and x suddenly becomes y. So let's say, okay, that means that we have q, x, and y, right? We see x appears in here. Well, let's replace that with, or this should be z, pardon me, q, x, z. Well, let's replace that x with q, y of z. This is totally valid, right? Because we don't need to prove this statement itself. There's no truthness or falseness or assignments or satisfiability requirements for this. We just show that it is the case, right? And this is the abuse of the axioms that we can use. This is part of axiom group 6. Because suddenly we can just use this to generate any well-formed formula that we want. Now then, something else from axiom group 6 that you might, actually, before I do that, the third step, we have, this is generalization in a nutshell. This is axiom group 2. Where is it? Here it is. So we can generate any well-formed formula that looks like this. And the reason we want to do that is because we know this, that all of these have universal quantifier. So in order to get a universal quantifier in there, let's use axiom group 2. So axiom group 2 states that if for all z, qxz, then, well, let's just pick a z. Let's pick z equals z, q, xz. This is part of axiom group 2. And again, I don't need to prove that I can use this. Because it follows the format of axiom group 2, we can just add this to our deduction however we want. I'm going to abuse the concept of axiom group 6 again. And I'm going to say x equals y implies, and then this is going to be a very long well-formed formula. This is going to be the well-formed formula that you will see that will look familiar. qxz, where am I? Gives qxz implies for all z, q, xz gives q, y, z. Where this is our alpha, this is our alpha there, we replace this with this. You might think, man, that's awfully convenient that this is, very closely related to, this is exactly our third line in our deduction. It's not convenient, it's on purpose, because we can have these be any well-formed formulas. And so it's most useful to us, if we're looking to apply modus ponens, to just have this equal to an existing well-formed formula. And therefore, we can just use modus ponens, right? By way of modus ponens, we have x and y. xy was the first thing we did. So we therefore have, for all z, qxz, then qxz, then for all z, qxz, qyz, by modus ponens on alpha 1 and alpha 4. And then from here, hey, we got this. Alpha 6 gives us, for all z, qxz gives qyz. My modus ponens on alpha 5, alpha 3. Now, we are very close, right? This here looks very similar to this, but remember, we're doing an I deduction, which means we're actually using here. So we're actually using this set of assumptions, and then we're trying to prove this. So normally, if this wasn't an I deduction, we would get stuck right here because we don't know how to add a quantifier to just this, right? We would have to maybe at most use an axiom group and put a quantifier and then distribute it. But that would give us two quantifiers here. It's a different formula. So what do we do here? Well, since we're using deduction theorem, we now know that this is part of our assumptions. So alpha 7, a little bit of an abuse of deduction theorem. We say that for all z, qxz is in our set of assumptions. And then it follows almost immediately that we have qyz by way of modus ponens on alpha 6 and alpha 7. We are now very close. We still need to add that quantifier. And how do we add this quantifier? Well, there are two ways to add this quantifier. The first one, where am I? Here. The first one is axiom group 4, right? But what is axiom group 4? Axiom group 4 is just generalization. It means that if alpha is true, then any generalization of alpha is true. So we can say that it is with axiom group 4, or I could just say actually, I could just say that the final step in my proof is for all y, q, y, z. And why? Because this is an I deduction, it's by the generalization theorem. Now, this is controversial. This is weird at best. So let's maybe not consider this. Because I mentioned before, I deductions are formal deductions, but with steps skipped. Whenever you use a meta theorem, you can just decompose that into its regular theorems. So instead, we will do the proper alpha 9. Let's say this is alpha 9 star, which is given some well-formed formula. We have the generalization of that well-formed formula. So given this, we have this. This is an element of the fourth axiom group. And then finally, rather than one step, we've decomposed it into two steps. We now have for all y, q, y, z by MP on alpha 8, alpha 9. So this is the end of our proof. Right, we have now shown that x equals y, and for all z xz, that we have for all y qyz, then by the deduction theorem, more specifically a deduction theorem on provability, we now have x equals y proves for all z qxz, that if qxz, then qyz. And that's exactly the end of our proof. All right. Was there any questions? Anything along the way? Nope. Everyone looks good. All right. In that case, I've already gone like about half an hour, 20-ish minutes over. So let's take a 5-10 minute break. And then in that time, Mark will take over. I think, Mark, it's probably best if you share your screen so I don't have to keep rearranging mine. But yeah, we'll take a 10-minute break. We will come back during that 10-minute break, maybe between 5 and 10 minutes because we're short on time. If you have any questions, just post them in the chat and I will answer them as best I can. Let's take a look. For alpha 9, axiom 4 requires y needs to not be free, whereas y is free in x, y, z. Step 9, y seems free. Can we use axiom 4 on free variables? Let's see. I might have made a mistake there. Let's take a look. Axiom 4, provided that x is not a free variable. So, provided it is a free variable here. Okay, so where's my cursor? Y is free, and it is free here. Okay, so small correction. There we go. Small correction. I can't use axiom 4 because axiom 4 requires free variables, and well, it's not free. So this is not the case. This still applies. But that just means that I have to abuse the concept of generalization, and I shouldn't give a reason for it. This actually ends up being exactly step 9. So yeah, step 9 means we have to generate this by generalization. But that gives us the same thing. This last step is probably the most informal portion of an informal deduction. But yeah, there's nothing else, nothing really else I can explain. This is the utilization of a meta theorem. This is the closest we have to a meta theorem. Another question. You have to use, oh, where am I? Also requires that y doesn't occur free, right? Actually, it doesn't. The generalization theorem, which I copied here, if we say that alpha is a generalization of gamma, if gamma is of the form x1 for all x1, for all x2, xn, where n is a natural number, and xi just has to be a variable. It doesn't have to be, it doesn't even have to be in the formula, but for the cases where it is in the formula, it still holds true. I'm gonna recheck that as well in my notes because I have a little bit more complete notes here. Every rule forms a generalization itself. Yeah, that's fine. Let's scroll down a little bit, check a little bit more. This is automorphisms. If you're wondering, I have my notes from this class pulled up somewhere, and I'm just reading through them. Yeah, it doesn't have anything about freedom. In fact, xi does not even need to be in the support of alpha. So, yeah. Generalization theorem, weirdly enough, doesn't require that y occurs free. So we have to use that. The other reason I know this to be the case is this specific step. There is an incredibly similar, there is a very similar question in the textbook that I do have bookmarked because I had to use that to find the proof for this one. This specific step, let's see if I can find it. Here it is. I'm assuming you all use Enderton's book. This specific step comes from Enderton, page 122. It's a deduction at the end of the page. This example isn't actually given a number. So, yeah, it's the unnumbered example step 5. Yeah, he basically just does the exact same thing. His predicate is P, not Q. He pulls the for all Z instead of for all Y. And then the reason he gives is axiom group 4 plus generalization. Yeah. I'm not sure about the not free bit, but this is pulled directly from the textbook, and so I assume it to be the case. The Y not free for axiom 4 is totally true though. Y cannot be free in axiom 4. But for generalization theorem, there isn't any restriction on it. Or at least I couldn't find any in my notebook either. All right, Mark, I guess when you're ready, you can share your screen to start. We still have a few minutes left for break, but yeah, about 2 minutes left for break. Just share your screen when you're ready.
I'm going to make you host because I realized that I probably need to share screen on my iPad, and I'm not sure if that's gonna affect when I log into Zoom on iPad. I'm not sure that's gonna hurt the meeting, so I'm gonna make you host for now.
Oh, yeah, sure. Okay. So then I will reshare my screen and I will just be, I guess, moving my screens up and down.
Oh no, it's okay. No, I should be sharing my screen on my iPad. I just don't want to. I'll join in Zoom again on iPad, but I don't
Oh,
want
okay, yeah.
because I might get disconnected. So,
Yeah, that's fine. Yeah, we're still on break, so.
all right, making a host. You have control over record.
Yeah, the recording is still going.
That's good. Yeah, so apparently my iPad will just take over my control, so I'll have to do it this way. Okay, so apparently the website got a little bit laggy, so I'm going to do my part on I'm gonna do my part on my iPad instead. Okay. Can I close this thing? Okay, maybe not. That's fine. So, do you think we're ready? Let me just see. It's a little bit hard because it's on iPad. It's a little bit harder to actually see everything now.
I think that's good enough. I'll keep an eye on the chat as well.
Okay. Yeah. Thank you. Okay. So again, thank you, Bob, for going through all of those. Those are my least favorite of this entire subject, but so it's good that Bob Hart carried that part. I guess I'll go through part that I'm personally more familiar with, which is going to be the definability section. So, what do we want to achieve with definability? Well, in essence, that we have for every single structure, for every single language, we have some predicates, we have some functions, we have some constants, and so on. And we wonder, what can we say? What can we concretely pinpoint with these things that we're given? So, for example, if I tell you that I'm working with the natural number, if I'm working with the natural number, say, and then I say I gave you a 0, and then I give you the successor function, which is the same as just +1. Well, then you can pretty much define every single number, right? Of course, I can also give you a whole bunch more. Say I can give you less than. I can give you the predecessor. I can give you equal, and so on. I can give you a whole lot of stuff, and but it turns out you don't really need any of the extra ones over here. You don't really need the one at the front. So that's what we're trying to figure out. What can be defined without any ambiguities. So yeah, let's try to think about it. So just as the other cases, we have to define some notions. We have to define some definitions. And the first one here is the free variable assignment, roughly speaking. And is that, I realize I probably have added for all assignment here. Okay. For all assignment, I will quickly add that. Here. Okay. So what we have is that, well, first of all, some of you might recall that in a sentence, the assignment doesn't really mean anything. A sentence is something where everything is quantified. So for example, for all x, for all y, there exists z, such that p, x, y, z, and q, z, or so on. So this is a sentence. We can see that every single variable has a quantifier in front. Of course, if we're being technical, this exists should be not for all and then not as everything afterward. But let's just assume we have those for now. So this is an example of a sentence. But we also, so if we have a sentence, the assignment doesn't really matter. So we're going to use the free variables in our formula to get the notion of assignment, and the notion of defining things, which is why over here we start with phi. I personally use phi, so sorry for the slight inconsistency. Let phi be a Wolfram formula with free variables. So we say x1, x2, all the way up to xn. Without loss of generality, we can rename these variables. They're not bounded anyway, so we can rename them to however I want. You can, of course, sometimes you can use the same name. For example, maybe you want to use one thing multiple places, then the same thing multiple places, then you might want to use maybe x1 in 2 places, maybe x1 equals to x, maybe for all y, x1 equals to y, and x1 equals to x1, maybe something like this. The meaning of the sentence doesn't really matter for now. So we give this notation, which is that under a particular, this has to be under a particular structure over here. And we say the top part, it's true if and only if for any assignment, if we assigned each variable with its according value, then that assignment will satisfy phi in the structure U. So this is really just a definition where essentially is saying, well, our S will name, our S will turn our bunch of variables, x, x2, all the way to xn, and then it's going to map them to a1, a2, an, and then we say, I believe the notation is goes like this. It's going to be true. Let's say if this, then this. Okay. So what about maybe another assignment that doesn't assign it as such? Maybe this one, it's not A1, but let's say constant. Our constant doesn't equal to A1. Well, just like in the tautological implication and so on, we don't really care. It doesn't satisfy the prerequisites, so we don't really care about stuff in this case. Okay, so this gives us a notion of assigning free variables value, and then talk about what happens when assign those with specific values. So now we can actually, now let's move on to the definition of definable. I'll give a copy over here. Let's just go back here. Write it down. Okay. So now again, the definability can only work within a structure. What we're doing is that we're saying, well, if we, under this language, if we give it a specific structure, what can I define in this structure? And over here, we're dealing with tuples once again. I personally use the angle bracket for tuples because brackets sometimes you use for grouping symbols. So we say that, first of all, we have a structure. We have a k, which is going to be some positive integers. And then we say, R is a subset of k tuples. So we can imagine R being equal to maybe the first tuple, A1, A2, AK, and the next one being B1, B2, BK, and so on. So we say, now we say this particular relationship, it looks like a relationship. We see this is definable if and only if for every single tuples
in here, there is a sentence such that for every single tuple in here, we can assign the free variable with the values, and it's going to satisfy the sentence. So we have to first say there exists a sentence. Well, sorry, not a sentence. If it's a sentence, then we don't have any free variable. A well-formed formula. There exists a well-formed formula such that a tuple, say A1, A2, AN, belongs in R if and I'm going to use the symbol here, if and only if this structure and this formula is satisfied when you using whatever assignment, as long as your assignment is going to be uses these exact elements that we used here. So, for example, what if I have maybe my R looks like something like this. So this is just a finite example. Well, if our R is like this, and let's say it's definable, then there must be a formula such that when you give a 1, 2, and you give a 3, 4, these two are satisfied with the given structure. Nothing else is satisfied. So such as, let's give 5, 6. This would not be, this is not, the truth assignment would not be true. Okay. I think these are the basic definitions. Also notice this is a subset of the universe to the power of 2 in particular. So obviously everything in here has to be the same arity. Okay. I'm gonna switch back just to see if anybody have anything to say. Okay. Oh, actually, I do have an example here. Let's take a quick peek at these couple examples. So here are some examples for definable relationships. First of all, is that we have this structure M, which we define it to be, its universe is going to be all the natural numbers, 0 as equals. And then we simply say, we give them the usual definition. So 0 is just 0. This is the successor function. Equal should be defined as it is. With this, we can say that every single natural number can be defined. Well, how do we say that? What do we mean by that? So we would say maybe our relationship for a particular number is just going to be, say, nothing but that particular number. So this is a unary tuple, so we can treat it pretty much. Maybe isomorphism symbol is better. We can say these two are practically the same. So we need to find a formula such that it has one. First of all, it has to have one free variable because this is a unary tuple. And second of all, the only way to satisfy that particular formula is by giving that free variable the value of n. Well, how do we do that? Well, I already sort of wrote it down here. We can write down our formula as such. Our formula is simply going to look like n, actually x1 equals to s followed by s dot dot s0, and over here we have n s's. I'm going to put a little bracket here to indicate that this is actually the formula that we're dealing with. Okay, we can pretty much check this pretty easily. We can check that, yes, for anything, if you assign this value, say, if you assign this value m, then m doesn't equals to the n on the right-hand side, so you're not going to get, your formula is not going to be satisfied. And if you do assign x1 with n, then you're going to be good. So we say, let's take a look. We say, so now we realize that, let's see, our formula, it's satisfied if and only if, maybe put this as a1, if and only if a1 equals to n. So remember, in this case, s have to x of x, s of assignment s of x1 equals to a1. So you can sort of relate these stuff around. I'm not going to use double symbols for logical implication. Okay. As for the other example here, we can also see that sometimes you don't need that much stuff to define concepts. We can try to define positive on the real numbers without using 0 or greater than equals to. And let's go through that quickly. So our structure is going to be the real number with a multiply and an equal. Notice that we don't have 0 or positive here. We say this is enough. I don't need any other stuff to define positivity. Of course, these all have the usual definition. Okay, so once again, we can define our relationship, which is going to be essentially all of the x, such that x is greater than 0. And our formula is going to be, there exists another number such that x equals to that number times itself. Well, we know every single positive number has a square root in R, so that's how it works. Notice if we use the same formula, it wouldn't really work if this is a complex, because you can have a negative complex number and so on. So -1 will have, say, I as in place of that k, and then you will include too much than you actually wanted to. So there are some examples of definable sets. And one thing I do want to mention here is that in some sense, you can write your formulas in a way so that maybe there exists something, and later on this k with a property, with some properties, and then now, assuming you bracketed everything, now you can refer to k again with those properties, and then you can sort of do that for groups theory. I believe I have an example later on that can talk about it. Okay, one quick thing before we finish off, which is this interesting corollary about something being undefinable. So far, we have shown two things that are definable, but of course, there are things that are undefinable. So, for example, let's just look at say whether or not we can define something on the structure of natural number. I'm not going to write down specifically what are the predicates that we're working with, because it doesn't really matter. So let's just consider all of the potential unary unary subset. So notice earlier here, this is a unary relationship. Let's consider all of them. So maybe one of them could be, say, just 1. Some of them can be 1 followed by 2. Some of them can be maybe all numbers, and so on. All of these are possible. So maybe this is R1, this is R2, and this is R3. Now, how many such relationships are there? If you do a little bit of set theory, you will know that, well, how many there are? Well, each one of them can be related to a particular subset of the natural number. And there's a bijection between them. So we know there's at least power set of natural number, many of them. Okay, so maybe let's just say it goes all, I'm going to do a little bit of abuse of notation, and then say maybe it goes all the way up to relationship power set of n. Now, how many do we have here? Over here, the size of it, let's say cardinality, what does it equal to? Well, it equals to the cardinality of the power set of natural. And this happened to equal to the cardinality of the reals. Now we start to see an issue, which is that earlier we defined something being definable if and only if there's a sentence, there's a formula that can describe it, right? Now, it is clear that if you have two relationships, you cannot have a formula that represents them in some sense, that represents both of them at the same time. Well, they're two different sets. That's the whole point. You have to use a different formula to represent them. But how many formulas do we have? Because formulas are all just finite strings, the collection of all finite strings only has, let's say, I believe the well-formed formulas, the size of well-formed formula is just the size of natural number. And now we run into the issue, which is that we don't have equality here. And in fact, it is strictly smaller. Real number is strictly bigger than the natural numbers. So that means even if every single formula defines a relationship, there are still relationships that we cannot define. And these are only the unary relationships. There's also binary, 3-tuple, 4-tuple, and so on. So there's so many things that are undefined once your underlying set, your universe, become too big. Of course, if your underlying universe is finite, then it depends on whether or not you have provided enough predicates and so on to actually define things. Okay, so this is pretty much the very simple the intuition behind definability. What we're saying is that we have a couple free variables. This is our formula. We have some free variables, and then we say the moment how we consider all the ways that you can assign these free variables values, and we say if the values satisfy this formula, then we say it is in my definable set or so on. Okay. Is there any questions right now? I'm gonna switch back to take a peek. What is P? Sorry, not explaining it earlier. This P here means the power set. So the P of 1, 2, 3 is going to equal to the empty set, the set of 1, the set of 2, the set of 3, 1, 2, 1, 3, 2, 3. And then 1, 2, 3. So if we're having a look, there's a theorem that says the power set of any set has strictly greater cardinality. If you're interested in the logic that you take, you can take D09 next term, which is an introduction to set theory. And you can learn more about it over there. That's fine. For the most part, you can just imagine that there's just far many ways of choosing stuff than there are things that you choose from. So you're going to have more stuff to count. But this is basically the point of this part is to motivate to think about, well, since there's cases where there are undefinable things, how can it determine what are those undefinable things, which is what we're going to go through coming up. But first of all, we'll have to take a little detour and talk about morphisms between structures, because that will be the tool that we use to talk about when is something undefinable. Okay, so this is going to be a more definition dense part, because honestly, there is personally I do not see any other way besides to just introduce the definition, but hopefully we'll take our time a little bit slower so we can actually understand them. I know we're running a little bit short on time, but I'll try to get us through in time. So we let U and B here be two structures, and they should work on the same language, right? That one's I believe sort of given in class. So we say a function that goes from the universe of U to the universe of B. It's a homeomorphism if and only if it satisfies the conditions. So let's first of all just quickly remember what is in our language. Our language has some constants. It has some predicates. It has some functions as well. And what's the point of a structure? A structure is to give these meaning, right? So over here, the CU here give these constants meaning in the universe of U. The CB here also gives same symbols meaning. However, the meaning can be in a different universe. So that's the difference. So our goal here is to translate meaning from one universe to the other universe. So what does that do? What do we have to do? We have to make sure that first of all, for all CI, HCU CI of U, I believe, is equals to CI of B. Now let's unpack this one, taking a little bit of time unpacking it. CI of U is giving the CI a meaning in U. So over here, this part belongs in the universe of U. Now H is a function from U to B. So this part is now currently in the universe of B. And obviously this belongs in the universe of B just because you're assigning it in the universe of B. So first of all, this equality at least makes sense that we're talking about the same thing in the same universe. And then what it captures as saying, the meaning gets translated over. You can send a constant sort of a couple anchoring points, say, these are the stuff that I know must be true and must have a certain behavior, so map them over one by one. Now let's move on to the function. We have for all f, H fu of this A1 AN equals to FB H A1 H A N. Okay, once again over here, we're talking about something that these stuff should taking stuff that are in U, right? I believe if I recall correctly, F should be something from UN to U. So our function should behave in a way so that it takes in stuff in U. This part spits out something in U. And once again, over here, we now translate them into B. Over here, each individual one are now suddenly in B. And then we say the whole thing's in B because that's how F in B is defined. So if you've seen stuff like group theory before, or maybe you have, I believe it might have even been in some linear algebra. This is similar to the following equations. H A plus B maybe equals to H of A plus H of B. You might have seen something like this, where over here, maybe it was a function that is in the first universe. Over here, this plus is a function in the second universe. So really, we should probably attach these with little subscripts to indicate that, hey, they're in different universe. Okay. Lastly, we'll quickly breeze through this for the predicates. Well, as Bob said earlier, the predicates, you can think of it as a set. So if you're in the set, then predicates spits out true. If you're out of the set, the predicate spits out false. Which is why over here, we see we're not defining a particular predicate. We're just saying, hey, here's a tuple that is in U. If it's in U, then after you map it element by element, it should still be true. It should be in a tuple in B. And then the mapping process should not change the truth and falseness of the predicate. And so that pretty much takes care of the definition of homomorphism. Maybe I'll just write this down. Maybe I'll just copy down this as well. A1, AN belongs in UN. Let's write it down real quick. A1, AN belongs in P, understood as in the universe of U, if and only if H, A1, H, AN belongs in the predicate understood in B. So notice this part is in universe U tuple. Over here, it is in B of N tuple. Okay. So now it's probably the most dense understanding. It's just some slowly build up. Essentially, we have homomorphism, we add a couple constraints, and then we give them different names because we need name for everything. That's honestly probably one of the hardest part of mathematics to me is to understand all of the meaning. Okay, so I think I will expand this a little bit because we don't need to write that much down, which is that we already know what it means to be a homomorphism. We add a slight constraint over here, say it's 1-to-1, and then we get isomorphism. If on top of isomorphism, we add this onto, then it's called an onto isomorphism. Now, this is a little bit different from many of the other fields where isomorphism already needs to be one-to-one and onto. That's not quite the case for our logic here, but it's the term that we decided to use, so I'm gonna have to stick with it, unfortunately. There's also one more definition of what it means to be isomorphic, which is that if there exists an onto isomorphism, then you say the two structures are isomorphic. What is a capture? Well, it captures that, first of all, you have the same amount of things. So over here, remember these two, we understand them as sets. And then this being onto and one-to-one in the set theory understanding is saying you have the same amount of things. You're not going to map two things to the same thing, and then you're gonna every single possible output can be reached. As for the homomorphism part, so remember isomorphism is homomorphism plus one-to-one onto. Let's just say this is one-to-one plus onto. What about homomorphism part? I should probably denote this set bijection. What about homomorphism part? The homomorphism part tells us that the way you give meaning to the predicates and the functions has not really changed when you go from one structure to another. Yes, the specific value might change, but then the meaning behind them hasn't really, because of the way we define our homomorphisms from before. As we've seen, we simply just say, oh, there's a function that translates from one meaning to another. And that's pretty much it. Then we get to a special part of isomorphism, which is called an automorphism. Do I have it here? I should have it here somewhere. Yes. Yes, let's quickly write this down. I knew I have it somewhere, just as a matter of where. Okay. Give me just a second. Let's quickly bring up to speed with automorphism. Well, automorphism is just an onto isomorphism with one constraint, which is that the input and the output has to be the same. That's all. But this turns out to be very useful when you're trying to show undefinability, which we will now bring in. In class, I believe Grinnell should have went through this theorem, which is that if you have an automorphism and then you have a relationship, that is definable, then before you use the automorphism, after you use the automorphism, a tuple should either stay in the relationship or stay out of the relationship. Now, the way to intuitively understand this with our previous understanding is, since an automorphism is an isomorphism, onto isomorphism, an onto isomorphism doesn't change the meaning of the predicates, the functions, and the constants, whether or not you apply the automorphism should not matter. And especially since our input output are of the same set, so you can actually make sense of this. Over here, we have something that is in UN. Over here, we still have something that is in UN. So that's the intuitive understanding. for the most part, I believe if he asks an undefinable relationship, it's most likely using this because we don't have too much tool beside it to actually work with. So why don't we go through one of the examples here? I will only copy the question. We can share all of these later on, all of these notes later on. But for now, let's just do the question together. Here is our example. Okay, here's our example. We're going to show that if your structure is somewhat restrained, so in this case, it will be R, 0, and plus with their usual understanding, then we're going to show that the less than is not definable. It's not definable. Okay, how we do that? Well, with the previous theorem we're given, we can try to find one such automorphism that violates this property. Well, what is that one such automorphism? Well, it turns out to be this one. First of all, obviously from R to R, we'll map every single element to its negation. Okay, there's a couple things we have to check, which is that preserve constants. Well, there's only one constant to check, which is a 0. And then they all have the same meaning. We just have to check whether or not it maps to the same one. Just say H0 equals to -0, -0 equals to 0. So what happens here is that we satisfy the first property. And then let's take care of function. Let's see. Let's say we have a function a plus b, the value of a plus b. Okay. Well, what is this equal to? It equals to negative a plus b, which equals to negative a plus negative b, which equals to h of a plus h of b. And we see that the function actually preserves the property as well. So if you have two things that adds to, let's say you have a plus b equals to c before, then your h of a going plus your h of b is going to equals to h of c. One last thing we need to check is the predicates. Luckily, there is none. So we don't have to check it anymore. So what happens now? This justifies H is an automorphism. Okay, now we have this part of our theorem. Now we just have to check the rest of it. And over here, we're going to use proof by contradiction. Thank you, Bob, for setting us up for all of that. So by contradiction, suppose the less than relationship is definable. Belongs in real square a less than b is definable. Then by previous theorem, we should have maybe, let's pick out a particular one. Let's pick out 1, 2. Let's pick out the element 1, 2. And we say 1, 2 belongs in, I'm going to call this relation. Let me just quickly rename this relationship so it's easier for us to talk about it. Belongs in the less than relationship should implies that h of 1 and h of 2 belongs in the relationship as well. However, what does this equal? This equals a -1 and -2, which doesn't belong in the relationship. And thus we have a contradiction, which is why, by contra, is not definable. I'm not sure if Ray has gone through this example, but then it's the one that I was given back then. We're running a little bit low on time. I'm going to try to go through the rest of it a bit more quickly. I see. So most of it, we actually gone through most of it already. So this is roughly.
Mark, I think you have a question in the chat.
Okay, thank you. Give me just a sec. It's a bit hard to see the two screens. It means suppose. Okay, I want to go through just a little bit because I think it's somewhat important since Bob also mentioned about model. And then if we have the time, I'll try to go through maybe one more undefinable example and then talk about maybe the intuition behind it. Okay. So let's talk about what this model thing is about. So I believe Bob already, as Bob already did earlier, talk about what model really is and the validity of sentences, formulas, and so on. Over here, we give a slightly different definition, I guess, which is that we say a collection, a model can be seen as a collection. What is a collection of? Well, first of all, it's a collection around a particular sentence. And then we say it's all of the structures that satisfy the sentence. Now, if you recall, since we're here, we require phi to be a sentence. We don't actually need any of the assignment later on because all the assignment will be overwritten by the capturing for all and there exists anyway. So that's the definition of this mod function. And then we introduce an idea of called elementary classes, which is saying a collection of structure is an elementary class if I can describe it by just one sentence. Unfortunately, I am not too well versed in this, and I cannot think of any elementary class that cannot be described by a sentence, but I feel like there's partly is, and I believe set theory can also answer some of those questions. Since Bob earlier mentioned about group theory, let's consider the following sentence, which actually I thought about it as well, that try to describe group theory in just one sentence. What are the properties of a group? Well, a group is a G equipped with an operation. This operation takes G cross G to G. This is called a closure. It's associative. Actually, maybe I should use multiply here, since I use multiply right above. It's associative, so A times B times C equals to A times B times C. There's also an identity element. associative. There's an identity element, let's say identity, such that for all x belongs in G, E times x equals to x times E. There's also an inverse, which is saying for all x belongs in G, there exists x inverse such that x times x inverse equals to E equals to x inverse times x. And that is, this E in particular is the E that was specified here. So what I tried to do is describe this whole thing inside of one sentence. First of all, the closure. The closure part is pretty much already given because the way we structure give meaning to functions already guarantees closure. You're not going to map to something outside of this universe. That's not happening. So let's take care of the first associative. And that's the first part of this sentence. For all three elements from my universe, the first two multiply and then the second one should be the same as the last two multiply and then the first one. Notice here we don't have the commutativity where x times y equals to y times x. That's by choice. That's just the definition of a group. And then we're going to deal with the second half of our thing. I say there exists an E such that for all elements, that element times C equals to itself equals to E times that element. That's the identity part. And then I have still this same X. I say there exists an X inverse such that X multiplied by that inverse equals to E equals to the other way around. And I bracket this whole part under this particular X. You can technically split out the second half, but I was saving characters. One more thing I do want to bring your attention to is that there's a reason why I bracketed all of these. As I said earlier, this particular E refers to this one. If I were to say there exists E such that there exists for all X over here, and then my bracket earlier over here, that would not be good. Because if I have, I should probably erase that. I should not have erased that if I say over here. Because if that's the case, this E and this E might not refer to the same E. And that would be a problem. We want them to refer to the same one, which is why I have bracketed everything behind in a single one. Oh. In a single bracket. And then because the exist has a highest binding, so which is all of these is binded to this particular exists. Okay. I'm currently over time, I guess. Is there any questions immediately? If not, I will stay around for a little bit, maybe goes through one more small examples for the undefinability. And then I guess we can stick around for a little bit longer. Okay, I will try to go through the last bit of the thing I wanted to talk about, which is an example I was thinking about when I was driving around earlier. It is another thing that I believe is undefinable, and it's because we're we have too little material to work with. So what I say is that my structure is going to be Z, all the integer, with the successor function. Nothing else, and nothing else. I don't have 0, I don't have equal, I just have a function. So my language is going to be tiny, right? Because I don't have anything. But we're going to show that under such circumstances, and it's just not definable. What is my h going to be? Well, my h is once again going to take, well, I am very restricted to where I can map it from and to, just z. And I'm going to take x to just x plus 1. Clean. H is automorphism. All right, I probably should have mentioned, we do have to mention that this is indeed, H is indeed bijective. Because otherwise it wouldn't be an automorphism. All right, we claim H is bijective here. I think this is this should not be too bad to understand, which is because our function is just doing this. We're just mapping everything forward. So it's going to be bijective. Constants, preservation, I'll check since there is none. Predicates, check, all done. What about the function? Well, all we have to check is whether or not H applied to the result of a S applied to something. Does this equal to applying the successor after the homomorphism? Well, yes, because this is just as a plus 1 equals to a plus 1 plus 1 which equals to the one above. There's really nothing much to say here. It is just, I just did some simple manipulation. Essentially treating bracket differently. Okay, so now with that, I can now claim that any single number, every single number itself, it's not definable. Now, why is that the case? Once again, let us suppose for contradiction, suppose relationship n equals to just the n is definable. Then let's say the element belongs in Rn. Then by the definability and then the fact by definability and this being an automorphism, maybe I should put a check here. Being automorphism, then h of n should belong in Rn as well. However, this equals to n plus 1. And since our Rn only has that particular n, it doesn't belong in the relationship. Rn, because of that, Rn is not definable. And in essence, both of these examples shows us that you have too little materials to anchor down, to force, you have too much freedom in your homomorphism because there's not enough predicates, constant, and functions to anchor down the meaning of things. So those homomorphism can just go all wild and just say, I send stuff randomly to like all over the place. And both of these examples shows that if you have too little stuff, some concept is just not quite definable because everything becomes too flimsy. And with that, I believe I have also covered most stuff I want to. I will combine this with Bob's PDF later on, and then we can share that somehow. Do you have anything to say, Bob?
I think that's good. But yeah, as Mark said, I have saved my portion as a PDF. Unfortunately, the software I'm using, the quality of which they can save large PDFs is incredibly low, so I've just been taking screenshots of them. And so you're going to see some very misproportioned pages in my half of the PDF. But yeah, I'm going to attach yours to the end so you have both halves. I'll send that to Grinnell. And then also this lecture has been recording, so hopefully once it's done recording, we'll also send the Zoom recording link to Grinnell and he will post it on Quarkus for you guys to reference. If it's not there before your exam on the 9th, or like a few days before, I guess you can keep pressing him and asking him about it. But yeah, we plan to send it at the very latest by the end of the day, once this recording finishes rendering. But yeah, that's about it. Thank you guys for sticking around so long. I know we went a little bit over time, and given the time constraints, we went pretty fast, but yeah, I hope this was helpful. Good luck on your exams.
If you are interested in more stuff like this,
take CO9 a second time.
Yeah, I mean, you can do that, but I mean, I think if you're very interested in stuff like this, where you find the course interesting, you can consider taking DO9 next term, which is set theory. You can also consider taking, as said before, philosophy C51, where they talk about the Gödel incompleteness theorem, I believe. You can also adventure into other areas like categories theory, another interesting subject. And I do have to show a little bit of my favorite subject, which is types theory. So for those who are more interested in computer science, there's some relationship between logic and the types of your functions.
For those of you also who are taking MATC09 set theory next semester, I'll be in your class. I'm also taking that next semester. And something I completely forgot to mention, completely skipped my mind during my portion. The 6 axial groups, I mentioned before, they can be interpreted both as sets of well-formed formulas and also statements in well-formed formulas themselves. If you take the intersection of all 6 axiom groups, you can say that is a well-formed formula, and any structure that models that well-formed formula describes a deduction in the first order. So in that sense, mathematical logic is also self-referential based on its own definitions, which is fun to think about. But yeah, anyway, with that aside, if there's nothing else, I hope you all enjoyed this. We will get those recordings and notes to you as fast as possible. And have a lovely afternoon.
Hope you all the best on your exam.